called FPT-time. And this is joint work with Anupam Advisor and Yu Lee, who was a PhD graduate last year. That's the info. So let's start with some history on the minimum k-cut problem. The problem is, given a graph, we want to split it into connected components, and we want to delete the minimum weight set of edges. Now this problem is studied in multiple different settings. The oldest setting is what do we assume k is anything? Could be as much as linear and n. In that case, it's a very simple approximation algorithm of Serrani, and it's greedy. We'll see this later on. And recently, last year, my neuroncy showed that a polynomial time algorithm beating two approximations and be hard assuming the small set expansion hypothesis. So, in other words, in the general setting, there's a matching upper lower bound, and these look pretty great.
What is the SSEH again?
Small set expansion hypothesis. So now the general is solved, but you might ask, what if we restrict k a little more and see if we can do any better? Can we, for example, can we beat it to a approximation? So what about in case of constant? Well, it turns out in a constant case, there's an exact algorithm, and it runs an n to the 2k time. And it's basically a generalization of Karger's mid-cut sampling. Now, more recently, there have been more work on this idea of fixed parameter tractability, which means you want your running time to depend on, it can possibly depend on k arbitrarily, like f is any function, possibly exponential. But the exponent in n should not depend on k. So for example, n to the 2k is not FPT, whereas 2 to the k times n cubed is n. So in this case, one question you might ask is, can we improve the exact running time of minimum k-cut from n to the 2k to something FPT? Unfortunately, the answer is no. Turns out the minimum k-cut problem is what's called W1 hard, which is a complexity class of problems that we do not believe are solvable in FPT time. So it's like FPT hardness. But that's pretty exact version. So one question we might ask is, second question we might ask is, what if you are allowed approximation? Can we run an FPT time and meet the two approximation lower bound for general k? In this talk, we answer this question confirmatively. We showed that we can beat it slightly in FPT time. And I guess the approximation improvement is small, but the point is, like, this is a proof of concept that if you run an FPT time, you can bypass lower bounds in the general case. So the rest of the talk will be high-level ideas of the algorithm, because there's not that much introduction. So at a high level, we're going to follow the greedy two approximation algorithm of Serrani. We'll see this later on. We'll make the following key observation. If the input graph does not have some certain specific structure, then we can modify this algorithm slightly and automatically cut in the analysis and get it to a minus epsilon approximation. Again, we'll see this later. In other words, we can improve the analysis slightly and squeeze in another epsilon factor in the approximation. And then that means that all instances where greedy does not do well must have this certain specific structure, which we'll see later on. And in that case, we'll provide a separate 2 minus epsilon approximation that takes advantage of the structure. Okay. So let's begin with the two approximation algorithm. This algorithm is just one line. For k minus 1 iterations, we greedily take a minimum global cut from the graph. Now, the graph might already be disconnected. So what I really mean is, I mean take the best cut of the graph that increases the number of connected components by 1. So we do this k minus 1 times, and that's our k. We want to show this is a two approximation. So how do we show this? So let's consider the optimum k cut, wherever it is. Let's suppose its components are S1 and Sk. Let's suppose we sort S1 and Sk based on their boundary size. So delta means the boundary of the side, the edges on the boundary of the component. And what?
Jason.
Yeah.
Justin.
Oh, you answered it. It's edge boundary, not vertex boundary.
Oh yeah. Like the edges that have exactly one endpoint inside of one endpoint. So one simple observation is, if we sum over the sides of the boundaries, we get exactly twice that. And the reason is because we take any edge in the optimum solution, it appears twice on the boundary, once on one side and once on the other side. So let's consider, what will our greedy algorithm do? Well, let's consider the first cut that greedy makes. Well, S1 is a possible cut for the first iteration. So greedy might do S1, might take S1, but it might take something else. But we know that whatever it takes must be at most the boundary side of S1. Now let's consider the second cut greedy makes. Well, in this case, let's consider the first two components, S1 and S2, in opt. And the key observation is that on the second iteration of greedy, either S1 or S2 is a possible cut for the second iteration. That's because if that were not the case, then that means S1 and S2 must be completely cut before. But that's not possible because greedy already made one cut, and doing so requires two cuts. So one of the two is not a possible option, and therefore greedy is at most the worst of the two outcomes, which is S2. And we can generalize this argument further, show that the ith cut that greedy makes is at most the boundary of Si, and therefore the algorithm cost, which is sum of the cuts it makes, is at most Si. So recall that the crucial part of our analysis was bounding the ith cut that greedy makes with the ith component in opt. What if we compare the ith cut that greedy makes with the first component in opt? Note that the boundary of S1 can be much smaller than the boundary of Si. So if we can tighten this bound to relate Ci to S1, then we can possibly get something much better. So that's what we'll do next. Suppose at some iteration we have that the cut that greedy makes is actually greater than S1, the boundary of S1. So what might such a case look like? Well, if we consider our graph, the claim is that before this iteration of greedy, S1 must have been completely cut before. Because otherwise, we can cut S1 and get one more component. Does that make sense?
Cut, you mean like, you mean all the edges?
All the edges have already been cut.
Okay. And
They weren't already cut, so we can cut the remaining edges and increase the number of connected components by one, so it's about.
But what if it hasn't been cut, but cutting it wouldn't increase the number of
That's
components?
not possible. If
Okay.
there's still one edge remaining, cutting will always increase. If you're cutting something
Okay, gotcha.
completely, then you will always get one. So that means the cuts that greedy makes must look something like this. So it must have completely cut the boundary of S1. It might have cut S1 into multiple pieces, and it might have made some cuts outside. But it's made at most k minus 1 cuts, because that's how many cuts greedy makes. So if we consider the components of opt, we consider the components of greedy, because at most k components, and we know the unit of some subset of these components, in this case these three, comprise S1 exactly. So this is a common technique in fixed parameter trackability algorithms, which is let's do some guessing. Let's guess which subset of components that we have comprise this. There are 2 to the k possible guesses, and one of them will give you the right answer. And then we can recurse. So our branching factor, our number of guesses we make every time is 2 to the k. And our branching depth is k, because every time we recurse, we decrease k by 1. We guess S1, and then we just recurse with k, replace k by k minus 1. And that gives us 2 to the k squared time. So times the polygon factor. This is if this is true. So that's pretty nice. Basically, this means that if we have this inequality at any point in the algorithm, we can apply recursion and with no loss in approximation because we guessed S1 exactly. So the hard case is when in which case the ith cut the greedy maze is at most the S1 boundary for all I. Of course, this is a much tighter inequality than this, what we originally had. So let's see if we can explore this further. Okay, so consider the following. Yeah.
Hey, sorry. What do you do after you actually say you successfully guess all the components whose union is S1? What do you do with that?
So you would just guess that as S1, remove out of the graph, and just recurse on the rest. Just call the algorithm, entire algorithm on the rest.
Okay.
But with k minus 1 or something.
With k minus 1. Yeah.
Sorry, I'm also confused about something. So you don't know delta S1 star, right?
Right?
So so every time I make a choice, I just randomly pick some subsets of the CIs that I've seen so far and just say, pretend these are delta SI, now let's continue. Is that sort of what you're saying?
I mean, you're going to fail all but one of the times.
Yeah.
But
Okay.
the point is one
One is
time
that one
works.
of them works. Well, get it.
Of course, here we need to find the case is small because our branching pattern needs to be bounded by k. So this will not work for large k. Okay, so let's consider the case where we take this much stronger assumption and see what the algorithm might look like. So let's plot two lines. The first line is the values of the boundary of SI are plopped. And the second blue line is the size of the cuts that greedy makes from 1 to k. Note that the red line is increasing because they're sorted, but the blue line can't go either. So then recall from our analysis that we have the simple assumptions that twice op equals the sum of the boundary sizes. Now it's helpful to think of this as the area below the red curve. Because that's like integral areas below the red curve is just a sum. And the cost of the algorithm is the area below the blue curve. And recall that the key observation in the 3D analysis was that the blue curve lies below the red curve. Now, what if we can do the following? What if there's a large gap between the two curves? Well, I claim that if there's a large gap of sufficient area between the two curves, like here, then we can indeed tighten the analysis and squeeze in that extra epsilon in the approximation. And we'll see this right now. So here's how we're going to construct such gap. We're going to take S1, the boundary size is S1, as say that's the black line. Note that we're assuming the following conditions, so all the blue stuff lies below S1. And let's take 1 plus and minus epsilon.
Is this chart for assuming a factor of 2 or something?
Oh yeah, well we're assuming the red curve, the area here, is twice opt.
Pardon?
We're assuming the area under the red is twice opt. So we're implicitly, we're implicitly assuming a factor of 2. Because the area below the,
You're counting it twice in
Yeah.
the red curve. You're counting the edges twice.
Yeah.
That's why it's bigger than the blue one.
oh they could, it's possible they're like, there's a small gap, like they're the same curve, but with still 2 approximation because the area under the red curve is twice opt, whereas the area on the blue curve is 1 times the algorithm cost. So here we're trying to find a gap, a large enough gap between the 2 curves. And we'll show this is enough to improve the approximation. So we take boundary of S1 and multiply by plus or minus epsilon, 1 plus or minus epsilon, and draw these 2 lines. Suppose we can do the following. Suppose we can draw the following 2 lines. Let's say this line is 0.1k, and suppose that the entire blue curve from 0 to 0.1k lie completely below the dotted lines. So like this stuff lies below the dotted lines. Now also suppose that the red curve lies completely above this following dotted line from 0.9k to k. In that case, the following 2 rectangles belong in our gap. And observe that the area of these 2 rectangles is roughly 0.1k times epsilon times the boundary of S1. And we claim this is enough gap, essentially, because, well, what's the algorithm cost? It's at most k times boundary of S1, because the blue line lies below S1, and there's K points here. And if we save this gap, then this gap is actually a constant factor times the algorithm cost. And if we do our analysis, recall before we had analysis, the algorithm is at most twice off, but now we insert this gap, and that gives us a 2 minus S1 approximation. Any questions?
So we only need one of those rectangles.
Yeah, yeah. I guess I should have said that. Yeah, we only need one of the rectangles. So in the hard case, both of the rectangles do not exist. So what might such a hard case look like? There's no such gap in either rectangle. So let's suppose it looks something like this, where the first blue point, is already within the rectangle, the dotted lines, which means we cannot fit any prefix rectangle here. And let's suppose that the entire red line is between the dotted lines, which means we cannot fit any rectangle here. None of the two rectangles will be valid gaps. So then what do we know? Well, C1 is actually the mid-cut of the graph because it's the first cut greedy makes, when the graph was just the original graph. And it's roughly the boundary size of S1, which is the black line. And that's roughly the boundary size of any SI, because those are the points on the red line. In other words, the boundaries in opt, the boundary size of the first k minus 1 components are all roughly min cuts of the graph, because all these points are roughly this point, which is the min cut of the graph. And so, in other words, the hard case is when if you take opt, and take k minus 1 components in opt, they are all near min cuts of the graph. Okay, any questions? So there's one more case we need to consider. So let's suppose, so it's well known that given the graph, we can enumerate in polynomial time all the near min cuts of the graph, like 1 plus 1.5 approximate near min cuts of the graph. And now suppose we do that, and then suppose we find two near min cuts that cross, like in the following sense. Well, I claim this is good for us. We'll see this later on. So if two min cuts cross, then suppose we just cut the two min. Let's suppose we cut the two near min cuts. This will divide our graph into 4 pieces, which means that the min 4 cut of the graph can only be better than the cost of cutting these two, which was roughly twice the min cut. Yeah.
Sorry, when you say two min cuts cross, do you just mean that the both of the components they induce intersect kind of?
Basically,
Or
all four.
It's not like they share a perpendicular or anything.
It just means that all four. So like when you take two cuts,
Yeah.
you get components. Basically, they produce 4 components out of 3.
Okay. Yeah, because I guess you can have two like that, sort of.
Yeah, and that'll be
And
3.
then we have 3. Okay.
It's 4 instead of 3, which is why here we do min 4 cuts. So in that case, here we can do the following. Let's griddily take the best min 4 cut. We pay twice the min cut of the graph for essentially 3 extra components. That's like roughly 2/3 of the times the min cut of G per additional component on average. That's good because if you compare this to greedy, which takes 1 cut and pays 1 times min cut of the graph for 1 additional component. This is like better. This gives you a 1/3 min cut benefit per cut. So that means if we can repeat this like 0.1k times like before, then we save some cost and factor. So that's a good case. So like the real hard case, there's like 2 assumptions essentially. First of all, if you take the optimum solution, the smallest k minus 1 components are all near min cuts of the graph. Again, this is a pretty strong assumption because we can enumerate over them all. And moreover, none of them cross. So if we enumerate over all near min cuts of the graph, they never cross. So what does this look like? Okay, first of all, right, so you can enumerate, there are only polynomial number of many of 1 plus epsilon number of cuts, so we can enumerate, and we can also enumerate them. And they don't cross, that means, it's well known that this means that they form what's called a laminar family, which looks something like this. So the blue and red cuts are all the near min cuts of the graph, and the red cuts are, let's say, long opt. So they don't cross, as you can see. And we provide a separate FPT algorithm for this case. It's pretty nice. It essentially reduces the problem into a pretty nice structure, and we can provide a separate FPT. How much time do I have left?
5 minutes.
Before questions?
After questions. You have 5 minutes to finish your talk and take some questions.
Okay, so so this part I did not present in Soga because we have more time. So let's see how I'll give a brief overview of how this algorithm works for a special case of them, which I'll call laminar K.
So this definition doesn't just, you're not just talking about planar graphs or something.
No.
So, and this is, I guess, goes back to the other question of 2 cuts crossing. It means that the partitioning of 1 cut intersects, so that if you take both of them, you get 4 classifications. If they don't cross, you only get 3?
Yeah,
or-
that's why it's good, because getting more is good. We pay the same, if we pay twice the min cut, we can get 3 additional components instead of 2. That's good for us. Because we make fewer cuts overall. So let's call this special case laminar K cut, where we're promised the graph has this laminar structure. And so there's a well-known theorem by Edmonds and Giles that says that any laminar family of cuts has a tree decomposition. And what does this tree decomposition look like? So every node in the tree, which we'll call a bag, is a subset of vertices, and the subset is partition of the vertices. Moreover, the edges in the tree correspond to the cuts in the family. What this means is, if we cut any edge in the tree, that splits the tree into 2 canonical components. Take their vertex sets, that corresponds to a cut in the family. And conversely, take any cut in the family, it can be obtained by cutting some edge in the tree. So it's a bijection. And moreover, the size of the tree decomposition is linear. So one example is like this. So it's a tree. All the bags have vertices and they partition. Some bags can be empty. And we can compute the structure in polynomial time. So note the following. The optimal solution has k minus 1 near min cuts, and they belong in this laminar family, which means they can be obtained by cutting some edge in the tree. So opt is actually corresponds to cutting some k minus 1 edges in the tree and taking their components, and that's your opt. Opts will always look something like this. So for example, these 3 dotted lines could be 3 components of opt. So our goal is to basically cut k minus 1 edges in this tree and do it in the best way possible. Minimize the number of edges going between the 2 different components. So as a simple case, let's suppose the tree decomposition is a star, so it looks something like this. In that case, what can we do? So here's an algorithm to do it. Let's contract all the bags into a single node. So for example, contract V1, V2, and V3 into a single node. Contract V7 and V8 to a single node. And then the problem becomes, remove the minimum weight set of edges to isolate k minus 1 leaf nodes. So now, all of these are all the leaves are single nodes because we contracted them. We just want to delete edges such that we isolate some k minus 1 leaf nodes. This is a much easier problem than minimum k cut. This problem resembles, it's essentially the problem of partial vertex cover, which is, so this problem is, given the graph and the value k, we want to delete the minimum number of edges to isolate some k vertices in the graph. It turns out this problem has a this problem can be solved, can be approximated in 1 plus, there's a FPT 1 plus epsilon approximation to partial vertex. So we can apply this and solve this problem. And in the general case, it's much more complicated than this, but essentially we also reduce to instances of partial vertex. Okay, so lastly, there's two open questions. One of them is, can we improve the approximation factor to something much better? Or can we improve approximation hardness results? For example, is it possible that we cannot beat 1.1 approximation in FPT-time? It's possible. And maybe a more ambitious goal is, can you find an FPT approximation scheme for FPT-time? What this means is, given any epsilon, can we find a 1 plus epsilon approximation to this problem in FPT-time? So note that I stated before that partial vertex cover has an FPT approximation scheme. And one question may be, does minimum K also?
We're over time, so I'm going to say if you have questions for Jason,